Voltage transfer characteristic of MOSFET is one of the most important concepts in analog and digital electronics. In this presentation, we will understand how a MOSFET inverter behaves when the input voltage changes and how this behavior is represented graphically using the voltage transfer characteristic curve. Introduction. Voltage transfer characteristic, commonly known as VTC, represents the relationship between input voltage and output voltage of a circuit. For a MOSFET inverter, the input voltage is applied at the gate terminal and the output voltage is taken from the drain terminal. By analyzing this relationship, we can study MOSFET operation as a switching device and inverter. VTC analysis also helps in determining switching behavior, gain, and noise margin, making it a very important concept in CMOS digital circuit design. MOSFET inverter circuit. A basic MOSFET inverter consists of an NMOS transistor connected with a load resistor. The supply voltage VDD is applied through the load resistor to the drain terminal, the source terminal is grounded, and the input signal is applied to the gate terminal. The output is taken from the drain terminal. When the input is low, the transistor remains off and the output stays high. When the input is high, the transistor turns on and pulls the output low. Therefore, this circuit acts as a NOT gate or inverter. What is voltage transfer characteristic? The voltage transfer characteristic is a graph plotted between input voltage on the horizontal axis and output voltage on the vertical axis. As the input voltage changes gradually, the output voltage responds according to MOSFET operation. This curve helps identify different operating regions of the transistor and allows engineers to evaluate switching threshold and circuit performance. VTC curve. The VTC curve shows three important behaviors. Initially, when the input voltage is low, the output remains high because the MOSFET is off. As the input voltage increases, a sharp transition region appears where the output voltage drops rapidly. Finally, when the input voltage is high, the output voltage becomes low. This nonlinear behavior represents the switching action of the MOSFET inverter. Regions of operation. The VTC curve can be divided into three operating regions. In the cutoff region, the input voltage is less than the threshold voltage. The MOSFET is off, no drain current flows, and the output remains approximately equal to VDD. In the saturation region, the input voltage exceeds the threshold voltage. The MOSFET begins to conduct, current flows, and the output voltage starts decreasing. This region represents the switching portion of the inverter. In the linear or triode region, the input voltage is high and the MOSFET is strongly on. The transistor behaves like a low resistance path, and the output voltage becomes nearly zero. Switching threshold voltage. An important point on the VTC curve is the switching threshold voltage, denoted as Vm. This is the point where the input voltage equals the output voltage. The switching threshold indicates the balance point of the inverter and plays a crucial role in determining noise margins and reliability of digital logic circuits. Applications. Voltage transfer characteristic analysis is widely used in CMOS logic design to evaluate inverter performance. It is also applied in digital integrated circuit analysis, switching circuit design, noise margin calculation, and inverter optimization. Engineers use VTC curves to ensure proper logic levels and reliable operation of digital systems. Advantages. Studying the VTC of MOSFET circuits provides several benefits. It offers clear visualization of switching behavior, helps in designing digital circuits, defines logic voltage levels, and enables accurate noise analysis. Because of these advantages, VTC is a fundamental analytical tool in electronics engineering. Conclusion. To conclude, the voltage transfer characteristic of a MOSFET inverter provides a complete understanding of inverter operation. It explains how the circuit transitions from high output to low output, identifies operating regions, and supports reliable digital circuit design. Mastering this concept strengthens the foundation for advanced topics such as CMOS design, VLSI systems, and digital electronics. Thank you.